So what we will do today, basically we will try to develop the corresponding linearized state space model for the third order model that we already developed earlier. Okay. So we will start from the third order model that we already have. And if we start with that, so the model that we developed earlier could be written in terms of the state space form in this manner. That is, we have some x dot, which was some function, nonlinear function, of course, of x and u, where x was the state vector and u was the input, could be a vector, and x dot is the first derivative of the state vector. And because that was a third order model, so we actually had the three equations, three first order ODEs like this. So we had omega base multiplied by omega minus 1. We had omega dot equals 1 upon twice h PM, that is the mechanical input to our single machine infinite bus system, PT, that is the electrical output. And then we had some damping power. So this thing over here, this was the damping power PD. The third equation was of the internal Q axis EMF in the transient mode, that is EQ prime dash. And that was TDO dash whole bracket multiplied by EFD minus EQ. So this was the third order model, specifically the differential equations. And we all know that within this model, we have some algebraic variables. So the algebraic variables were PT and EQ over here. The model had two inputs. The first input was the PM, the mechanical power input. And the second input was the excitation voltage, or some transformed form of excitation voltage, that is EFD, that is applied to the DC field. So to complete the model, what we did, we actually expressed these algebraic variables in terms of some other variables like this. So PT was VDID plus VQIQ, where all these VDID and VQIQ are basically the components, D and Q axis components of the terminal voltage VT. And EQ was EQ dash plus XD minus XD dash into ID. And of course, we went further to express ID, IQ, as well as VD and VQ in terms of state variables, because ID, IQ, VD, VQ still they were not in the form of state variables. So that we also had some expressions for this, like VD was XQ IQ and VQ was EQ prime minus XD prime ID. And we also had some expressions for ID and IQ, little longer expressions. So overall, this model over here that I have written, this was the third order model for SMIB. This is third order nonlinear model. And this was the representation for this. So what we do today, we would like to express the same model in terms of some matrices and vectors. So our new model that is the linearized model, would be of this form. And we will call this the linearized version of the nonlinear model. So we'll call this linearized state space model. And to complete the model, we also have to complete this. So the output equation or the output vector equations, that is Cx plus du. So this would be our total model, okay, where these A, B, C, and D all are matrices, constant matrices, or matrices with constant entries. So why we need to do that? I mean, why are we migrating from the original nonlinear model to a linearized model? Because we want to apply later on the linear control technique, which is comparatively far more easier compared to the nonlinear technique, nonlinear control technique. This is one. Another target, we could also mention it like we want to actually analyze the small disturbance stability. And for that, we would like to have a model where the variables itself within the model, they state variables themselves, they are of small deviation type, okay, or small signal type. Of course, when we talk about some small disturbance model, we have to derive the model with respect to certain operating point. So the small disturbance model or the linearized model, this model over here, of course, this has to be derived with respect to certain equilibrium point or operating point. And depending on the choice of this equilibrium point or operating point, actually the linearized version of the steady space model of the original nonlinear model, they actually vary, or their response varies, their characteristics varies, their analysis varies, okay? So that's why fixing a certain equilibrium point while trying to derive a linearized model from a nonlinear model, it is very important, or it is imperative to fix a certain equilibrium point, okay? In other words, we can say that the linearized state space model is only valid in the vicinity of a certain equilibrium point, okay? Let's look at some example, or at least one example for that.
Sir, I think your voice is a bit not
Is it low or broken?
low, sir.
Is it okay now, or still it is low?
No, sir. Now it's okay.
Okay, I will try to continue at this level. Let's see. Okay, so if I want to explain now what would be the problem, or what is the issue with fixing a certain equilibrium point for a linearized model, or for a linearized version of a nonlinear function, let's say. So let's say I have a function, sinusoidal function, which is f of t, and I take this one. So if I want to, okay, first of all, is it a linear function or a nonlinear function? So the function expression is simply function of t is sine of t. Okay. So is it nonlinear? Is nonlinear or linear? Okay. So the answer should be nonlinear. How do you check it? Simply you go for the tests that which are associated for checking whether a system or a signal is linear or nonlinear. Simply you have to go for two tests, okay? The homogeneity and the additivity. So if both of those are satisfied, then you say that the system is linear, otherwise it's a nonlinear system or nonlinear function. So in this case, it would be a nonlinear function. Even with those tests, you can justify the answer. So if I want to have a linearized model for this, what I said is that we have to fix a certain equilibrium point. So if I look at the function closely, then I would find that I have just taken intentionally a single cycle, okay? Because it is a repetitive, so 0, pi, and twice pi. If I look between 0 and pi at the initial point, if I extend it a little bit, it should look like this. So this zone, can we say that it is more or less a linear zone within the original nonlinear version? So if I take this range of values for t, can I say that, well, I can establish a relationship between this ft and t, which would become a linear function? Can I? The highlighted portion in green. Yeah, it is more or less linear. But of course, it is a zonal behavior. Okay, it's not universal. It's not a global behavior. Again, so if I say, well, I can get some equation because it is going through the origin. So of course, I can get some form of equation like this, isn't it? To represent this with a certain slope. So a straight line going through the origin where m is the slope of this. Is the slope positive or negative?
Positive.
It is positive. Excellent. So let's say we fix the origin as our equilibrium point in this case. And we can say, well, around the origin, we can have some linear relationship between ft and the t. However, if I choose pi as my equilibrium point, I might end up with another linear portion more or less like this. Okay. So around this equilibrium point pi, I might be able to find another straight line relationship or a linear relationship between ft and t, however, with a different slope. So what would be the slope here for this one?
Negative slope.
It's a negative slope. So you can clearly see, if I change my equilibrium point from 0 to pi, so if I shift from 0 to pi, if I am at 0 and if I say, well, I have got a linearized version of ft, well, that is true. But in that case, I have got a slope with a positive value. However, if I choose another equilibrium point for the same nonlinear function ft, I will end up with another linear version of the expression ft, but now I have a completely different characteristics with a negative slope. Okay, and probably if I extend it, I will, of course, I will get some expression like y equals mx plus c, or y1 equals m1 x plus c1. Okay, so the behavior of these two, or the relation, or the expression of these two, of course, they are different, their slopes are different, and later on we might find that for a stability related analysis, this choice of equilibrium point is very, very important. So that's why fixing an equilibrium point for getting a linearized version of an original nonlinear system is very, very important. Okay. So with this little introduction on the necessity of choosing an equilibrium point before we try to linearize a nonlinear model, let's go and try to find out what would be the way for linearizing this block over here. Of course, there were two more equations, ID and IQ. Okay. So for linearizing this set of equations, what we would like to do, of course, this is in the form of f of x. This is in the form of f of x equals x dot. And of course, we have some u here, so better we include it here. So this is in the form. And here, what we want the linearized form, and that would be x dot equals ax plus bu. This is our target. To achieve this target, what we will do, we will simply take help of Taylor series expansion. and truncation of the higher order terms. So what we would do, we would first like to express our nonlinear equation or nonlinear model with the help of the Taylor series expansion. And because we will be looking for the linear terms, so any term that will appear after we take the Taylor series expansion of the nonlinear expression, any term that would appear to us to be nonlinear, we would simply truncate them. And we will call them higher order terms. So in general, for any single variable expression, for any single variable expression, of this form, so we had x dot equals f of x. We would assume first that we have some equilibrium point for this nonlinear system, which is this one. So f of x0 is 0. Okay, so that means what? That means x0 dot equals to 0. So these are the two conclusions. And this variable x, which was in our original nonlinear model, we can express it with the help of our equilibrium point x0 and some deviation, small deviation from that, that is del x. So if we replace this now into our f of x expression, what we will get is this f of x0 plus del x. And then if I apply the Taylor series expansion, what I would get is this. So it would be simply f of x dot plus, because it is a single variable, so it would be better to use simply d over dx, df over dx evaluated at x0 multiplied by x minus x0 plus 1 upon factorial 2 d square f over dx squared multiplied by x minus x0 whole squared plus some more terms, which are of course of higher degree than 2. Okay. Now, if I'm interested only in the linear part of this, only in the linear part of this right hand side over here, and I also know that at the equilibrium point, my function value would return 0. So I can simply write f of x0 is 0 plus df over dx. I have to evaluate it at the equilibrium point. And this x minus x0, I can get it from here. So I would write x minus x0 equals to del x, the deviation variable itself, plus 1 upon factorial 2 d square f over dx squared into, again, we have x minus x0, so we can simply write it as del x squared. And of course, some higher order terms that would go for cube of del x, then to the power 4 of del x, and so on. Now again, if I am only interested in the linearized part of this expression on the right hand side, this part is 0. This part is, I have to evaluate the first derivative of di f, that is the original function with respect to x, and then I have to evaluate it at x0 at a certain equilibrium point. What about this? Is it a nonlinear term or a linear term? And another thing, what about the magnitude of this and any magnitude that would arrive here in the higher order terms? That means in the higher order terms, I expect to have del x cube, del x to the power 4, del x to the power 5, and so on.
Sir, if our del x is very low, then the higher order terms will be essentially close to zero. The cube and to the power 4 to the power 5.
Excellent. What about this one? Del x squared.
Sir, I think after differentiation, I'm not sure about if it will be still be linear or non-linear.
Okay, so because our model, ultimate model would be, ultimately we will see that our model would be in terms of del x, okay, the deviation variable. So what we can say, okay, let us continue. Let us keep it for the time being. One thing is for sure, that the higher order terms, I mean, if I go further, I will, because del x itself would be a very small deviation from the equilibrium point. So if I go up to any higher expressions or higher degrees of this del x, of course that would vanish to zero. Okay, so we just ignore them, we just truncate them. Now what about the left hand side? The left hand side, what do we have? We replace this x dot by this. So we have got x naught plus del x. We can write it like this: 0 plus di f over di x, x naught del x, plus of course this one, which is causing some problem. Okay, let's keep it. Should be d square f over dx squared del x squared. We don't repeat the remaining part because we agree that that would be 0. What about this one?
So this is 0.
This is 0. So you see, ultimately what we are left with some deviation, some derivative of the deviation variable, okay, del x dot. So the system would be ultimately represented in terms of del x dot equals a del x plus something. So that means if I now try to compare this with this that we have over here, we can't allow anything like del x squared, del x cubed, del x to the power 3, and so on. So ultimately, by truncation, we mean that we also have to truncate this non-linear term. This is a non-linear term because of the squared, okay? Because of the appearance of the square, del x square, this is a non-linear term for our model. So we actually truncate here, okay? So the thing that is ultimately left, the terms which are ultimately left is df over dx evaluated at x naught multiplied by del x. And that means actually we have got a model something of this form: x dot equals ax, because it was a single variable. I mean, we only considered some state variables. There were no u variables or input variables. So ultimately we end up with x dot equals ax. Okay. Any question here? No question.
Sir, I have a question about the operating point. I mean, how are we choosing the operating point very close to x naught?
No, we are not choosing the operating point very close to x naught. X naught is our operating point actually.
Okay.
X naught is the operating point, because it is very easy to find out x naught. Why? Because the function of x naught, sorry, the function of x naught would give me a 0, isn't it? As we have shown here. So function of x naught equals to 0 means what? This is okay, this is function of x and u. Okay, when I say function of x and u equals to 0 means what? The left hand side over here goes to 0, right? So that means this is 0, this is 0, this is 0. And we actually did this while we tried to find out the initial condition, if you remember. So the determination of the initial condition is basically another way to say that that is the determination of the equilibrium point. Do you get it now?
Yes, sir.
Okay, thank you. So if you don't have any other question, then let's continue with a multivariable multivariable case for the Taylor series expansion. Specifically, if we have some input besides the state variables, that is more analogous to our case here for the single machine infinite bus system. So if you don't have any input to your system, then this would be the expression in the linearized version. However, if you consider some input or multivariable case for this, so x dot equals f of x into x of x comma u. So this would be simply, you can now express it again, x 0 dot plus del x dot in the same manner. However, on the right hand side, now you have to write it like this, f of x naught u naught plus, okay, we have to make it die now because we have two different sets of variables, x and u. So you have to make it die f over die x evaluated at x 0 into del x plus die f of die x die f of die u evaluated at u naught multiplied by del u plus higher order term means del x square, del u square, del x cube, del u cube, and so on. So these higher order terms would be truncated. We will not include them. And again, by definition, this, we can also say that this f of x0 u0 is the same as this, okay, x0 naught. So we can cancel them out from both sides. And then we'll be left with this. So del x dot equals die f over die x, that is evaluated at x naught multiplied by del x, that's the deviation variable, die f over die u evaluated at u naught multiplied by del u, that is the deviation in input. And in short, now this can be written as a del x plus b del u. Okay, so we have actually got what we were looking for, this thing.
So this time our x naught dot will not be 0, like
no, it would be 0, but I'm saying in another way. Like you see, if f of x function of x naught and u naught, what is this? This means that the x dot is evaluated at x naught, isn't it? So this thing and this thing are actually the same thing. If you fix a certain point, your general model is this, x dot is f x u, okay?
Okay, yes.
If you say x0 dot, it would be what? F of x0 u0. This is what I said.
Yes.
That's it. That's why I'm canceling from both sides. But actually they would be 0. Actually both of them would be 0 because those are equilibrium points. So even if you calculate their values, ultimately you would it would give you a 0 value. So this is for the form. We have del x dot equals a del x plus b del u. I mean, now if you take, well, if you don't want to use this del every time, then you can simply say, well, x dot is ax plus bu, but implicitly this x and this u, these are deviation variables. Okay, in the linearized model, these are deviation variables. These are not the actual variables. That means these are not delta. So in this case, your del x dot would be what? Del delta. If I take del delta dot, del omega dot, and del eq prime dot. So this would be your state vector, derivative of the state vector on the left hand side. If I go further and if I want to express the x vector, what is x? Or what is del x actually? Del x would be simply del delta, del omega, and del eq prime. What would be del u? Del u would be, we have two inputs. First one is PM, so we have to write now del PM, and the second one would be del EFD. So these would be the variables that would now appear in our expressions, okay, in the linearized version. So whatever we have discussed till now, now we would try to apply this knowledge to our linearized model over here. Okay. So now let's go let's go and try to apply this knowledge to our original nonlinear model. So let me stop this share and start a new one. Yeah. Do you see this one? Linearized state space model of SMIB system.
Yes, sir.
Is it visible?
Yes,
The
sir.
PDF. Okay. So the top part is actually what I have already discussed. So this one already being discussed. This one already discussed. We have said that, well, we have the third order model with this set of equations, that is PT equals VDID plus VQIQ, and ID and IQ I actually didn't remember. So there you will get the expressions. ID again expressed as EQ dash minus VB cosine delta divided by XD dash plus XT, and IQ is VB sine delta divided by XQ plus XT. And omega base is the base frequency, which is 2 pi f. So now we have to find out actually which of these variables or which of these expressions should go for linearization. Okay. So let's go one by one. So the first one that comes in our way is this PT. Okay, this is an algebraic variable. So PT is a function of VD, ID, and VQ, IQ. And we know that VD is XQ, IQ. And VQ is EQ dash minus XD dash ID. So that means if I want to find del VD now, what would be that? XQ, what is XQ? Is it a variable or a constant?
Constants.
It is a constant, so we don't have to bother about constants, and we are only left with IQ. So we can simply write it as del IQ, okay, in terms of the deviation variables. Actually, what I'm doing is this. If I want to express it, what is actually going through in between, I can simply write it like VD0 plus del VD, okay, equals X cube, because it is a constant, so we don't bother about that. It will remain there as it is, because it is in a multiplied form, so it will remain there in the multiplied form. IQ, I would like to express IQ like IQ0 plus del IQ. Okay. Then VD0 plus del VD equals XQ IQ0 plus XQ del IQ. So we know that at the operating point, VD0 should be equal to XQ IQ0, isn't it? So what we are left with is simply del VD equals XQ del IQ. So here I'm only writing in, let's say, in very short, without explanation. And this is the explanation actually in between what is going on internally, okay? So it's pretty straightforward. Simply you replace the variables, the original nonlinear variables, VD and IQ, by their corresponding expression in terms of the equilibrium point and the deviation variable, VD0 plus del VD. You do the same for IQ, and then you simply check which are equal. So you know that at the equilibrium point, they should be equal. So VD0 is XQ multiplied by IQ0. So you cancel them out and you are left with del VD equals XQ del IQ. This is what I have written over here at the top. So this is in the linearized form already. So del VD is XQ del IQ. If we apply the same logic, we can also get something on the right hand side. What would be EQ dash? EQ dash.
Del EQ dash.
Del EQ dash, because it is a state variable. So it would only be AQ dash, del EQ dash. XD dash, it is a constant, it is a system parameter. It would remain as it is, and simply ID would become XD dash del ID. Okay, done. So now we see still that we still see that we still have the del IQ here and del ID here, which are neither state variable nor the input variables. So what we have to do, we have to again go for the linearized representation of IQ. So we start from IQ to find out what is del IQ. So what is IQ? We have the IQ over here, which is VB sine delta divided by XD dash plus XT. So if I write del IQ, then in the denominator part, basically it is simply we can say some constants. What is VB? Can you recall what is VB? So everything is gone with the Eid vacation, it seems. No problem. VB was the infinite bus voltage magnitude, okay? And by definition, infinite bus voltage magnitude and angle, they remain constant. So VB is a constant term. So we will not bother about this. So we'll keep it out of our linearization part. So we are left with sine of delta. So what we have to do now? So you have to calculate di f over di x evaluated at x naught multiplied by del x. This is the term that would come over here. So that means my sine delta, di sine delta over di delta evaluated at delta naught multiplied by del delta. Okay, this is what we will do now. So what would you get out of this? If you take the partial derivative of sine delta with respect to delta
naught, so
cos delta and evaluated at delta equals to delta naught multiplied by del delta. Excellent. So this is what we will get. Clear? This is about del IQ. What about ID? ID is not this one. So what is ID? ID, we have EQ dash minus VB cosine delta divided by, oh, I think I made a mistake here. So just sorry for that. Let me erase this. This is XQ plus XT. XQ plus XT. Then we have ID in the denominator, we have XD dash, in the numerator we have EQ dash minus VB cos delta XD dash plus XT. Now tell me, what would be del ID? The denominator, we keep it out of the linearization, and then what would happen with del EQ dash? Again, it is a state variable, so simply we can write it as the deviation variable del EQ dash
plus
minus. Okay, so you can do it at once.
Plus VB cos
VB sine.
So sine delta naught del delta.
Okay, so this is what we will get. Okay, following this expression over here. So we have seen that IQ, ID, VD, and VQ, all these are now in terms of the deviation variables. If we want, we can use some different notations now, just to simplify the expressions, which you will find in the later part of this slide. Okay, the second page of this slide. I will keep up to this point here, and then when I will explain from the slide, then I will show you.
Could you show again? I mean, the double ticked part. I mean, how did you replace del IQ with that one, sir?
Del IQ.
That expression. Yes,
this
sir.
one.
Yes, sir. With that expression of
okay.
DDX of.
This is on the right hand side. Remember, this is on the right hand side of the Taylor series, not in the left hand side. In the left hand side, we have to write x0 plus del x. Okay, x0 dot plus del x dot equals, then you apply the Taylor series expansion and you only keep the first term. I mean the second term. First term goes to 0. First term goes to 0, so this one goes out. Okay. And yes. then I said, well, so this you have to calculate in this manner, because now you have some sine of delta. Okay, so the sine of delta, you can take the Taylor series expansion of sine of delta, and then you have to you use this part only, because sine of delta 0, as we agreed that at the equilibrium point, this part is basically f of delta 0, isn't it? If you only pick sine delta as your function, so this should be 0. So what's the next term in the Taylor series expansion? The next term is this, di f over di x evaluated at x naught multiplied by del x. So f here is sine delta. Okay, f here
Yes.
is the sine delta. So I'm taking di f over di x. X is delta. So di sine delta over di delta evaluated at x naught. X naught means it is delta naught multiplied by del x. For us, it is del delta. This is how I'm doing it. Okay.
Yes.
Okay. Any other question? Because we will now quickly move on with the remaining part of the linearization. If not, then let me erase this and let me move on. So we are done with the parts required to express PT. You see, we have expressed VD in terms of del VD in equation 4. We have expressed ID in terms of del ID. We have expressed VQ in terms of del VQ, and we have expressed IQ in terms of del IQ. So if I replace all of those now into this expression, I can get del PT. Okay. So this is more or less done. What about this PD? What would be del PD? Anyone?
So T del omega minus 1.
D del omega minus.
So T multiplied by del omega. Yes.
Okay, what is D? D is the constant, okay? Damping power coefficient. It is a constant. So when you linearize a constant, actually you get nothing out of it, because you have to take the partial derivative and you can do this. So this would be actually 0. So you'll be only left with D del omega. Okay, it means what? It means actually you can write PD, you can expand it like D omega minus D, right? If you just expand it, remove the bracket, then delta PD is what? D is a constant coefficient into del omega. Omega is a state variable, so you take the deviation variable, minus it is a constant, let's say 5 or 6 or whatever. So if you take the derivative, partial derivative, you actually get nothing out of it. Okay, so that's it. So D being a constant would not give you anything in the linearized version. So it is simply del PD equals to D del omega. What about these EQ? EQ dash plus XD minus XD dash multiplied by ID. So what would be the linearized version? Del EQ is simply del EQ dash. What about this? These are constant system parameters. And what will happen with ID? Simply it would be del ID. And we already have the expression of del ID. So we can replace it here, and then we will have the linearized version of del EQ. So that is done. Anything else remaining? The first equation is remaining actually, because we started from here. We are done with this. Now delta dot. So what would be del delta dot? What is omega base? Omega base is simply 2 pi f. It is a constant. So we can write del delta dot equals omega base into del omega minus, what should be there?
0.
0 should be there, because omega base is a constant. Okay, so that means your first equation would be simply del delta dot equals omega base multiplied by del omega. The next few equations requires a little bit more attention, and we will continue with that in the next slide.
So you said you showed EQ dot, EQ dash dot. Did you show that?
Well,
mean, you
EQ,
showed that.
no problem. Yeah, we can continue with that. Del EQ I haven't completed this. Okay, I haven't replaced everything there. I'm just saying few things. Okay, let's continue. No problem. Del EQ dot should be would be what? What is EFD? It's a state. Is it input or is it a constant?
It's a constant, sir.
No, it is the input. Remember, we have two
Sorry,
inputs, PM and EFD. So this would remain there. If it were constant, then it would have become 0. Okay, in the linearized version. But it is one of the inputs. So we have to keep it minus del EQ. Minus del EQ would come from here, and that's it. Okay. Of course, you have to replace del ID that we already have derived earlier. So with this, now let's see how we can simplify a little bit our expressions, and we can have a more structured way of representing the linearized version of the third order model. So the basic of linearization is done. We have shown how to apply those. Okay. So what they have done, in the later part is this. Okay. So what I have shown is actually up to this point till now. So what they would do, they would take 1 upon xd dash plus xt as multiplied by VB sine delta 0. So this is your C1. And C2 would be what? C2 would be simply 1 upon xd dash plus xt. This is just for, you can say, simplicity of representation, nothing else. Okay. So C1 is and in this case, C1 is a coefficient, which is this expression VB sine delta naught xd dash plus xt. Now, is the C1 constant or is it a variable? Let's check. What is VB? VB is the infinite bus voltage magnitude. It should remain constant. So this is a constant. Divided by xd dash plus xt, these are system parameters. They will remain constant. Sine of delta naught. Delta naught, once you fix your equilibrium point, delta naught becomes a constant. So overall, this whole expression for C1 would give you a fixed value, a constant value for a certain operating point, of course. What about C2? C2, it's very clear that it is a constant. It is simply a function of system parameters, the reactances of the system. So what they have done, they have actually included another line just to simplify the notations. So del ID is C1 del delta plus C2 del EQ prime. Next, we go to IQ, linearization of IQ. So the first line probably was done by me. The second line, the simplification term, you will see here. So it is a little bit more, you can say, it's much simpler than del ID, okay, because we have only a single part. So what is C3 here? What should be C3 here?
VB cos delta naught divided by xq plus
VB
6.
cosine delta naught divided by xq plus xt. So this is your C3, excellent. Multiplied by del delta. Is it a fixed value or constant value? Yes. Once we fix the operating point, we know what is delta naught, and that should be fixed throughout our analysis. So VB is a constant because it is the magnitude of the infinite bus voltage, and xq and xt, these are system parameters. So this should be constant. So C3 is a constant. What about VD? Del VD, we found that it is xq del IQ. And what is del IQ? Del IQ is C3 del delta. So we replace del IQ here by C3 del delta. And then we take xq C3 is P1. Remember, all these are done just to simplify your representation, nothing else. Okay, so P1 is nothing but xq multiplied by C3. P1 is another constant. VQ was linearized in this form, del EQ dash minus xd dash del ID. So we have to replace del ID. And del ID in the previous page, we saw it was C1 del delta plus C2 del EQ prime multiplied by xd dash. So, and then you just group the variables. So we have two sets of state variables. Del delta is one of them. Del EQ prime is another of them. So if you take common del EQ prime, you are left with 1 minus xd dash C2, And for del delta, the term that comes, that is minus xd dash multiplied by C1. And then again, this is your P2. And this is your P3. Okay, so you look, it's pretty simpler now. Just you say del VQ is P2 del delta plus P3 del EQ prime. Next is EQ. And EQ is the linearized version of EQ is simply del EQ dash plus XD minus XD dash multiplied by del ID. What is del ID? Again, del ID is C1 del delta plus C2 del EQ dash, XD minus XD dash remains as it is, del EQ dash remains as it is. Then again, you group the variables. Again, you have two variables, two state variables, actually, del EQ dash and del delta here. Again, you group whatever you have with del EQ prime. So you keep them together, and you again group whatever you have with del delta, you keep them together, and you name them as K4 and this one as K3. So del EQ becomes K4 del delta plus K3 del EQ prime, where K4 and K3 are again some constants. Of course, they depend on the equilibrium point or the operating point of our analysis. So del EQ is done. We have got some K variables now, or the K constants. What about PD? Simply PD is del PD equals D del omega. No further simplification is necessary here. What about PT? So for getting the value of del PT, what you have to do is this. So you see, now you have multiplication of variables, okay? Multiplication of variables. So we have PT. Our original PT was this, VDID plus VQIQ. So what you do now, you'd simply apply UV formula, okay? So if you apply UV formula, you simply get this. So out of these two, VDID, you get VD0 into del ID, then you get ID0 into del VD. Okay, this is UV for the first part over here. For the second part, again, there are two variables, VQ and IQ, both are algebraic variables. So again, you take VQ into del IQ plus IQ0 into del VQ. Any question about this part? No question. Another way you can also write it like this. Okay, I can also write it like this. PT0 plus del PT is the left hand side, and then you simply represent everything like this. VD0 plus del VD. You get the idea? ID0 plus del ID plus VQ0 plus del VQ plus, multiplied by IQ0 plus del IQ. Okay. And then you see it is VD0. If you multiply, remove the bracket, VD0 ID0 plus VD0 del ID plus ID0 del VD plus del VD del ID plus VQ0 IQ0 plus VQ0 del IQ plus IQ0 del VQ plus del VQ del IQ. Now tell me what is next.
So del VD del ID and del VQ del IQ should be 0, as both of them are close to.
We can, this is one way. Another way is this. So what you said is this, because these are multiplication of two small deviation variables, so these are very negligible. Okay, so this can be approximated equal to 0. About this one, VDID plus VQIQ, this is nothing but PT0 at the operating point. Okay, so if you cancel it, you can cancel it. So you see ultimately what is left, what is written over here. Del PT equals VD0 del ID, ID0 del VD plus VQ0 del IQ, IQ0 del VQ. Okay, this is one way to explain this. Another way, simply you say it is UV formula of differentiation, chain differentiation formula of U multiplied by V, two variables. Okay, so this is done. So we can erase it. So once this is done, then we continue with our derivation of linearized version of del PT. And what we have to do, we have to simply replace these things. We have to replace del ID, del VD, del IQ, and del VQ. Remember, VD0, ID0, VQ0, IQ0, these are nothing but the variable values at the initial condition that we found already in our earlier classes. Okay. That means the value of VD, ID, VQ, and IQ for a certain operating point, and that is our initial equilibrium point. So now, if we continue, so simply you replace del ID by this, C1 del delta plus C2 del EQ prime, and del VD is P1 del delta, del EQ, sorry, del IQ is C3 del delta, and del VQ is this P2 del delta plus P3 del EQ prime. Again, you will see that, well, we only have two state variables there. One is del delta, another one is del EQ dash. So you just group the variables. And ultimately you find that del PT is again K1 del delta plus K2 del EQ prime. So this K1, K2, K3, and K4 in the literature, they are known as simply K constants. Okay, K constants for a single machine infinite bus system. Even for multi-machine system, they use the same notation, the K constants. So in general, these are known as K constants. So up to now, what you have learned is how to derive actually the K constants for the single machine infinite bus system, third order model. Okay. So after all these are done, now we are in a position to represent our system, that is the SMIB system, in the desired form, that is del x dot equals A del x plus B del U. That was our target to start with. So let's see whether we can achieve that target or not. So to start with, we have del delta dot, that is omega base del omega. So what we have done, simply we have listed all the three linearized version of the equation. So the first one was delta dot. So this becomes del delta dot is omega base del omega. Del omega dot was the second equation. And this del PM, del PT, and del PD, if we replace them, of course, del PM is the input. So it remains as it is, one of the inputs, of course. Del PT is K1 del delta plus K2 del EQ prime, because there is a minus before that del PT. So they two also have minus signs before them. And del PD is PD del omega in equation 17 over here. So you see D del omega with the minus here. So that is done. First one is done. Third one, 1 upon TDO prime del EFD minus del EQ. What is del EQ? Del EQ already represented in terms of K4 del delta plus K3 del EQ prime. So del EFD is one of the inputs. So we leave with this, minus del EQ is minus K4 del delta minus K3 del EQ prime. So now we see that if we combine these three, and if we try to write them in terms of matrix representation, so we can simply write on the left hand side, this is our del x dot. So this is del delta dot, del EQ prime, sorry, del omega dot and del EQ prime dot. These are my three state variables in the deviation form. Okay, deviation from the equilibrium point equals. So now you do the matrix and vector multiplication. So this over here, this is our A matrix and this is our B matrix. This is the X vector, this is the U vector, and this is X dot. Of course, I am dropping the delta term over here. Okay, I'm not repeating those deltas here and here and here, but there are deviation terms, delta terms there. So simply you now write these three equations, 19, 20, and 21 in terms of AX plus BU. I hope you can do that. So once you do that, then you will find that this is your A matrix and this is your B matrix. The first benefit of linearizing the system, of course, with respect to a certain operating point we will see today, is that simply if you take this A matrix, and if you know all these values inside these, all these 9 elements inside this, if you simply type eigen of A in MATLAB, command prompt even, by putting all these values K1, K2, K4, D, and K3, and TDO prime and omega base, you will get the system poles. Because the third order system, you will get the system poles already calculated for you. So now, if these are the system poles, that is the eigenvalues of the system, that means if you plot them, and if all of these poles are lying on the left half of the S plane, this is sigma, this is j omega, and this is your S plane, complex S plane. So what should be the conclusion? If all the three eigenvalues over here for your system A matrix that is calculated over here, if you get all the three eigenvalues to the left of the imaginary axis, what is the conclusion regarding stability?
The system is stable.
System is stable. Excellent. If any of the poles are here, if any of the poles are here, let me draw it. If this is the case, let's say we have a complex conjugate pole on the left hand side of the S plane of the imaginary axis. On the right hand side, we have one RHP, right hand pole. What is the conclusion?
For some value, it might be unstable.
Not for some value. For any value, it is unstable.
Okay.
Actually, for any value, it is unstable. So even let's say a 100th order system. Okay, 100th order. This is a third order system. Even for a 100th order system, I mean a very big system, even if you have a single pole on the right hand side of the S plane, that is enough to make your system unstable. Can you explain why? A single pole on the right hand side is enough to give you the unbounded response or unstable response. Okay, let me give a little glimpse on this because we are running out of time, but I will finish with that. I will end up with that. Okay. If you remember, in your undergrad level courses, you used to solve something like this: y double dash t plus 5 or 3, whatever, 5y dash t plus y of t equals something, 0 or something. If you do you remember this?
Yes.
Complementary integral, complementary function particular integral. And ultimately what you did, you used to find out m1, m2. And ultimately you used to write for the final solution y as a function of time as a to the power m1x plus a to the power or b to the power m2x. Do you remember these things?
Yes.
Okay. And this was your final solution. Now let's say we have a second order system. Let's say these m1 and m2 are nothing but the poles of the system or the roots of the characteristic polynomial for this equation. Okay. So what you did actually, you applied the Laplace transform. If there were any initial conditions for the system associated, then you would also include that in the expression and then you used to solve it. This was in the undergrad level, where m1 and m2 were our desired roots. So if now you see, if m1 and m2 are positive, what would happen to this? Oh, sorry, this should be, okay, let's make it function of time because I wrote it in terms of time, not x. So a e to the power m1t plus b e to the power m2t. Now tell me, if t tends to infinity, what would happen to yt? What would be the response?
So if either M1 or M2 is positive,
Yeah, both.
then
Yeah, any of them is positive. Let's say any of them. Let's say M1 is greater than 0, M2 is less than 0.
so in any positive cases, the output will
In
also.
any positive case, YT would also tend to be 0, because e to the power plus infinity would be infinity. Whatever remains for M2, whatever happens with M2. Actually, if M2 is less than 0, you will see that if you plot it, if you say this is Y1 and this is Y2, the two parts of it, and this is your total Y. So you will finally see that, well, one of them would decay, which is associated with M2. We are calling it Y2. So this is Y2. This would decay ultimately, because you have e to the power some minus, let's say 2t. Let's say M2 is minus 2. And M1 is simply plus 1. M1 is simply 1. So what would happen? So actually, it would become infinity, okay? It would go to infinity. So what would be the resultant? The resultant would be, although the first one, that is Y2, it is decaying, but the resulting value would go to infinity. This is why even a single positive pole, even a single positive root for a dynamic system is enough. That is, I'm talking about this. That is enough to give you an unstable or unbounded response, okay? So in general, if you have hundreds of poles here, a to the power m1t up to, okay, let's make it a1, a100, e to the power m100t, even if this is the case. So even if m1 is positive and the remaining 99s are negative, so what would happen? Similar kind of thing would happen. The single unbounded response for this y1 is enough to take all the 99. Let's say all of them die to 0, all of them die to 0. But because we have to finally add up this one and the remaining 99. So the total response YT would give you an unbounded response. So this is why even a single pole is not good for a system, a dynamic system, a single pole on the right hand side. Okay. So in the next class, we will try to code it in MATLAB, and we'll try to find out the eigenvalue of A. We'll try to calculate all these coefficients K1 up to K6 in MATLAB domain, and we'll see how we can go on with the calculation of eigenvalue. And then of course, we will apply the Euler code that we used for a nonlinear system simulation. We'll also use that for these three equations now. And we'll try to also find out the time domain response. So we'll see in both ways, with respect to eigenvalues in frequency domain and in time domain with the help of the Euler code. Okay. So thank you very much. Any question? No question. Okay.
Sir, I had a question. Time allows it.
Yes.
We're always talking about selecting the operating point. I mean,
Yes.
how do we select it? I mean, is that arbitrary, or is the operating point a defined point?
Okay. So it will take maybe 2 or 3 minutes. Do you have the patience?
Sir, I have.
You have the patience. What
I
about
don't know.
others? Okay, if anyone loses his or her patience, they may leave, because this is his personal question, but let me try. The question is, we are always talking about some equilibrium point, okay? So let's say if I use our own example, very own example of single machine infinite bus system. How do you find out the equilibrium point, or what is so special about the equilibrium point? This is xt, this is xl1, this is xl2, this is our generator. Okay. Whatever, this is our generator. So now what is actually meant by equilibrium point or the operating point specifically? Equilibrium point or operating point means that is one of the steady state points that your dynamic system may actually take. Okay. For example, because we're talking about dynamic system, and specifically what is so special about the equilibrium point is this. Let me first tell this, and then I will go for how to find out the equilibrium point for our system. For a linear system, for any linear system, there is one and only equilibrium point. This is the beauty of linear system. This one of these special characteristics of a nonlinear system. One of the very special characteristics is it has multiple equilibrium. It will always have multiple equilibrium. Now, again, if we simply take the example of a sine, the first cycle of a sine curve, okay? Now, what are the equilibrium points? How to find the equilibrium points? The equilibrium points are those points where if you take the first derivative of the function and you equate it to 0, okay?
Okay.
So now you get it. How do you find out the equilibrium points actually?
Yes,
This is the way. So for this case, for the very simplistic case, these are the equilibrium points. So however, so you see in a nonlinear, this is a nonlinear system, okay? This is a sine function. You already have got two equilibrium points, of course, of differing characteristics. So you have to actually fix before you analyze the system stability, before you control, before you design your control system for control for any system, whether it is a nonlinear system or whether it is a linear system. You have to actually identify, or you have to fix this equilibrium point for which you are going to design your control system, let's say, because in general, if you're talking about linear system, again, either you linearize with respect to this or you linearize with respect to this, okay? So you have to find out which equilibrium point, or for which equilibrium point you are going to design your control system, or for which equilibrium point you are going to analyze the open loop stability or closed loop stability. For our case, the equilibrium point is simply could be found by simply taking, let's say if it is the nonlinear model, delta dot is something, omega dot equals something, eq dash prime is something. Simply what we did, we actually took everything equals to 0 on the left hand side. Sorry. So delta dot equals to 0 equals to whatever we had, we wrote it. Omega dot equals to 0 and eq dash equals to 0, equals to whatever we had on the right hand side. Okay. That is to say, let's say, for example, if now at the certain instant, your load demand for the single machine infinite bus system is such that you require to supply PE equals to 1 per unit, QE equals to 0.25 per unit. Okay. This is one sort of example of the equilibrium point. So that means to supply PE equals 1 per unit and QE equals to 0.25 per unit, what would be the values of other remaining variables internal to the system, or the values of those variables which are not specified? So you have to calculate those values, and we did it when we calculated the initial condition for this model. Okay, if you remember. Now let's say for any other instant, for the same SMIB system, single machine infinite bus system, of course the load will not remain constant, isn't it? The load will never remain constant, it will change. So yes, let's say for some other PE value, now the load has increased, P equals to 0.5, Q equals to 0.1. The reactive power demand decreases, real power demand increases. Of course, the values of VD, ID, VQ, IQ, everything will be changed, isn't it?
Yes.
So this is what is the importance of equilibrium point. Depending on your operation, at which point you are operating your system, your equilibrium condition or equilibrium point will actually shift from one point to another. Okay. And how to find it? Simply, the simplest way is to take this, make everything, all the dynamics would die out to 0, where you have the equilibrium as we have here. So the derivative, first derivative would go to 0. So these are the first derivatives here. We take it to 0 as a group. and then we solve the system remaining parts of the equations. You get it?
Yes. And
Okay.
for our case, if we get multiple equilibrium points,
Multiple equilibrium point, we will not take it because that is the topic in nonlinear control system. This course will not cover it.
so that's why we made our system linearized. So
This
that
is
we
this
can-
is one of the reasons. This is one of the
one
reasons.
of the reasons. Okay.
Yeah, this is one of the reasons. Okay. Any other question?
No, sir. Thank you.
No, sir. Thank you. So, okay, inshallah, we will meet in the next class on Friday and we'll try to code it and calculate the values. And inshallah, we'll try to find out the eigenvalues and the time domain response in that class using MATLAB. So till then, stay safe and stay happy. Okay, assalamu alaikum.